Check. We're good. We're here. Everything's rolling. Okay. Man, what a day. It's been a crazy morning. It's just one of those like ultimate wake up and just everything is just going crazy all morning. You know what I mean? Maybe don't. Hopefully you don't know what I mean today. That would be great. Don't know what I mean today. Uh but I'm here mostly on time. I mean 4 minutes late. I mean it just I'm here. So, hope you're doing well. Hope you had a good weekend. It it's been busy. It's been very busy. Hi, awesome. Okay, York Titan OM chiller. So we can dive into that. I see that question come in. I do have a fun fact I want to share. It was just an interesting thing. So I've been going back through the YVAA manuals, and uh, I want to follow up on that. Um, I haven't posted anything on like the community page for the channel so far. I was going to last night and then just ended up not getting to it. It's some interesting things, kind of the difference between the Model A and Model B. But so the OM, man, I wish I was supposed to get a schematic, wasn't I? Dadgum. Sitting here thinking about that. I'm pretty sure that was on my. Was that on my list? No, it wasn't on my list. Maybe that's why I forgot it. I need to add that to my list. We'll talk about the OEM here in just a minute. Let's go ahead and dive in. We'll get straight into my first point about just kind of our fun fact for this week and really important distinctions between the Model A and or Style A and Style B of a YVAA air-cooled screw chiller by York. And so the Style A was that's the one I've spent the most time working on, which was the first version they came out with, and they have since come out with the Style B. I personally have not. Let's see. I think I've seen a Style B in the field. I wasn't there to work on it. I was just looking at it. Right? No. I take that back. I've not ran into a Style B in the field. So all of them I've seen personally were the Style A, which is what I basically learned on in terms of what a YVAA is. Now, when they went to the Style B, they made a significant change in how the machine functions and is laid out. There's two very dramatic changes that have a complete rewrite of what the machine does. So let's come over here to our first one. This is a Style A machine. Okay. So this was the very first one they came out with. So we have our compressor. This is our refrigerant circuit. We come over to our oil separator, through the condenser, and then back over to our flash tank. Okay, so we have a condenser drain valve, right? Which on the older models with like the YCIV, this would have been referred to as a feed valve, but it's referred to as the drain valve in the YVAA series. So this happens through our flash tank economizer, goes through the economizing process, and then we had a fixed orifice right here on its way to the falling film evaporator. And they actually reference the the falling film evaporator in the Style A as a more of a true falling film. And if I'm not mistaken, it appears looking at like so one of the ways you know a falling film is how low the liquid level is in the evaporator. And on the Style A's, they had the sight glass like really far down. Like it's down really close to the bottom of the barrel. And that's where you tried to maintain liquid levels. About half of that sight glass, 1/3 to 1/2, was kind of the target for these machines. Um, so I'm honing in on this because this will be a key point here in a minute. So we have a falling film evaporator, and then we come back out into the suction, back to the compressor. So again, this is a Style A. The oil circuit itself is basically the same. So we have our eductor line pulling off, sending oil back to the suction line on this particular system. And we have our oil separator, oil input circuit, all that relatively the same. Well, we do have an EXV on the leaving side of the flash tank that was metering flow, this is how we controlled flow coming from the flash tank to the compressor. All right. Now, let's go look at a series B. We're going to see some significant differences here. Put that back. So when we look at this, let me kind of give you a layout. So this would be our compressor. This is our oil separator, condenser. This is our evaporator. Okay, so these are indicating like heaters. Right, so this would be an in-bell heaters. This is our body heater that wraps around the evaporator. Okay, so let's kind of track through this circuit a little bit here. So this is our discharge line coming out. We still have a muffler. We come into the oil separator. So we have our standard oil return line coming back to the compressor just like normal. All right, that's the same as the other machine. And then leaving the top of the separator, again, this is the same so far. We come out and go into our condenser, and you'll see that this has a T right here. So this is our hot gas coming off of the discharge, superheated discharge vapor back to the adductor to then get our oil return. All right, so oil return circuit, that's the same. They made it look slightly different. So in the Style A technically did have the hot gas line coming off of the compressor initially, but they ended up having to do a field modification where it came off of the discharge line over here because they kept cracking the pipe over here due to vibration, and they were sending too much. The discharge gas leaving this compressor was too oil latent, from my understanding. So they needed to get it over here, or one, it had less vibration, so it didn't break off. But two, we had better oil return because we had less total oil getting sent with that vapor. Okay, so one distinction between the schematics, but in real life, you shouldn't really notice much of a difference. Now, this is where this does change. On the Style A, we had a EXV in our liquid line leaving the condenser. We do not have that on the Style B. Okay, so that EXV on the Style A was referred to as the condenser drain valve. But we also had a flash tank, and we don't have that on this machine. We have a brazed plate economizer. So this economizer is going to function in a similar way to what you would expect to see out of like a Carrier air-cooled screw. Okay, those also use a brazed plate economizer. So do the Dunham Bushes. Those are brazed plate economizers. I think, let's see, who else uses that? Either way, those are two good examples. Carrier and Dunham Bush are two that also use this. It would be easy to reference material on. Why is let me see the question here. Why the oil sump tank freeze? Yes, so we do have oil separators on the YVAAs. Yes, so most of these air-cooled screws or just most screw machines are going to have an oil separator, air-cooled, water-cooled. The only machine that has a built-in is the handbell compressor. So the handbell still has an oil separator, but it is built into the compressor housing for the handbell series. Handbell's not the only one that has a built-in separator. It's just one of the more common ones we'll see in the field. And then your question about the oil sump tank getting freezing up or condensating, I will circle back to that in just a minute. All right, so we have this brazed plate economizer. This means that we're no longer using flash gas or a flash tank in order to have our economizing. So we don't have what we're doing instead is we are taking this liquid leaving this condenser is already subcooled to a degree, maybe 5, 10 so degrees. And then as we come into the brazed plate economizer, this is where we start feeding into our um, uh, we start feeding back to the evaporator, right? So the goal of this economizer is not to flash off the liquid refrigerant going to the evaporator, but it is to increase its effectiveness by removing more enthalpy. Again, we don't have to get crazy off into that if you don't want to. I'll just throw the words out there, and if you have questions, feel free to ask them. Ultimately, what I'm saying is we make the refrigerant do more work by increasing its subcooling. So let's say, just to give you some ballpark numbers, let's say we had 10 degrees of subcooling coming into this braze plate. We may have 20, 25 degrees or so leaving this braze plate, something to that effect. So, that deeper subcooling then processes back over to the evaporator through our primary evaporator metering device. And I'm saying this wrong. This comes over here. So this line here comes into the braze plate, comes out, and then we have our evaporator metering device, which is an EXV after the economizer. Okay, so on the Style A, we had a drain valve, which is an EXV, and then a fixed orifice, right? So we had these two working in conjunction with the flash tank. With the Style B, we have a single metering valve leaving the economizer, then feeding into our, and they call this one a true hybrid falling film evaporator, which means that we're running higher liquid levels in the evaporator than we would normally run with a standard falling film. So it's the same exact style that you would see on like a YK centrifugal, if that means anything to you, if that's something you've serviced. Same fundamental style. And when I see the schematic differences between the two, Style A and Style B, it appears to me that the evaporators they're using on the Style B do maintain a higher liquid level than what I was seeing on the Style A machines. And just the way that the piping and the internal baffling layout looks based off of their manuals and documentation, that would be my expectation, is you would see slightly higher levels on these evaporators compared to Style A, which we would also see in the sight glass. All right, so these do have a sight glass on them, and that sight glass, I believe, is probably a little bit higher up on the barrel, but we're shooting for the same thing either way. We do still want to maintain about 1/3 to 1/2 glass on these evaporators if we're properly charged and everything's working properly. So one primary EXV feeding to the evaporator, and then we do have another EXV actually down here. So this line right here, this is our economizer line. So this would be a T coming off of the main liquid line, feeding into a little small EXV. This EXV is what feeds the cooling circuit of the economizer line. All right, and I can show you what that EXV looks like. Got it pulled up here. So this is they show it's a Danfoss, so it's just a little small valve. That's where your wiring would connect to, but it's still doing superheat control on this machine. So this would be the EXV. You're going to see this little stainless steel module there in that liquid line feeding into the cooling circuit of the economizer, and then based off of superheat control, it will then control how much feeds through that EXV and then back into the suction, or I'm sorry, back into the economizer port on this compressor. So this circuit does feed back into an economizer port separate from the suction line, so it doesn't come back to suction. And that is because we are still using an intermediate pressure. So keep in mind that the saturation temperature on this braze plate is not, it is not at suction pressure. Okay, suction or evaporator saturation, right? This actually runs a higher saturation because that's all we need it to do, right? We're not trying to get 45-degree saturations for our liquid line. We're trying to get down, I think the manual said it's trying to achieve 1.2 times the evaporator saturation as kind of its ballpark set point. So whatever, it's, if you're running a 45 degree, multiply that by 1.2 or so, and you would expect the economizer intermediate pressure or intermediate saturation to be in about that range. And then we're coming into I think it was 1.67 times suction. So basically quite a bit of the way through the compression cycle of the let's see, of the screw bolts, right? So what I mean by that, let's come over here. So these compressors, we have our suction, and then we have our screws here, and then our discharge, right? So that economizer port is right here, and it's feeding into about this range. So our suction gas is coming into here and getting swirled up or getting brought through the screw bolts that way. But this economizer line is, and this is true for either machine, by the way, so this is just how these CTS this isn't even specific to these CTSs. This is how screw compressors with economizers, whether they're flash tank or braze plate, this is how their economizers work. So we're bringing an intermediate pressure in, and it's kind of hitting about this zone of the screw bolts and then compresses the rest of the way. Again, there's a lot of fundamentals as to why we do that and why that saves energy. All of that is what I get into and cover in depth in my chiller certification course. So like all of these big terms or names that I'm bringing up as I'm going through this, all of this gets broke out into a lot of detail, and I take it piece by piece. My goal for right now is I just wanted to show you kind of two critical differences between a B series and an A series, or style A, style B of a YVAA, and you would expect them to function quite a bit differently because of that. So that's my goal right now. Anyway, so this is where we have a standard economizer line coming into the screws, but we have an intermediate pressure here, which we also have that same basic function with the flash tank, right? So that part of the process hasn't really changed. It's just that we're increasing subcooling. Instead of trying to use a flash tank, we're doing a braze plate heat exchanger. We have I would call it a non-standard EXV. So this valve here does not look like a normal valve we would expect to see. It is just a little small, bullet valve, if you will, a little small thing. But then the primary EXV is a standard EXV. And then that feeds into our evaporator. Now, something else to note with these machines, these evaporators are separated. So they're ran in series with each other between circuit 1 and circuit 2. So you're actually looking at what would be one circuit's evaporator. And then over here, there would be an independent evaporator for the other circuit that are tied in series. So it flows into one circuit, flows through that heat exchanger into the other heat exchanger, and say all these are in a 2-pass configuration. So it makes 2 passes through, makes another 2 passes through, and then comes out the other evaporator. That's how these will be designed, and that's how you'll see them piped in the field. And that is different than what we saw with the style A machines, where both circuits shared the same evaporator. Okay, and the evaporator on these was split down the middle, if memory serves. So they were cut, the evaporator was split in half internally, but they all shared the same evaporator shell and whatnot. That's on the style A, whereas the style B, we actually have independent evaporators. And that's so if you want to know which style you have, those are the two big things you're really looking for. Is one, do I have one solid evaporator or two independents that are ran in series? And do I have a flash tank or a braze plate? Those are the key things you're going to be, and that's going to change significantly what potential problems you could have, how you're going to need to troubleshoot this, and just, yeah, how you expect this machine to function. Like, this has a major impact. So that's kind of our fun fact spill I had for launching this stream off, and just kind of some reading I'm doing and kind of getting into the differences. So this is my first time reading the Style B manual. I've heavily gone through the Style A machine over time, but I hadn't really gotten into the Style Bs, and honestly, I just didn't realize just how different they were. I like what York did. For the way that the YVAAs function, I do think this is probably a better design overall on the Style B. I don't even know if they're making the Style A's anymore or if they're still in production or not. So that would be a fun curiosity. If anybody knows, is the Style A still in production? That is a community post I do plan to put out there sometime this week. You may even see that this evening. But I'm very curious if that's even still a thing. Well, this solenoid valve installed on the oil sump. Yeah, so on that oil sump question, do we have a it's used for on the oil sump question, do we have a specific model? So you're mentioning that there's a valve installed. So that could mean different things depending on what machine you have. Like Train has a vent valve on their oil separators. Or I'm sorry, on their oil sumps, their tanks, which you did use the word sump tank, so that would probably make me think you're dealing with a Train. But so do Yorks also have some oil solenoids as well. So if you wouldn't mind specifying what model of machine you're looking at, that'll help me give a better answer. Familiar with the Train, uses VI to increase velocity in low load and low ambient conditions. Is York doing the same thing on these separate? Yes, exactly. Their step VIs are doing the exact same thing. It's just to maintain velocity and flow through the compressor at unloaded conditions, which specifically low load conditions with low ambient conditions, right? So if we're in a situation where we're trying to maintain, we've got lower head pressures due to low ambience and we've got low load conditions, we've got to be careful because we get into this place where if we don't maintain the velocity correctly, we lose the ability to control oil. And so oil flow, oil return back to the compressor, like our oil management side of the system begins to fall apart in those situations. That is why they have the VI option available, so that in those low ambience with low loads, if we're running in those environments, we've got to be able to maintain oil control, and that's what gets a lot of machines in trouble. Most of the time when we do run into a oil issue with a lot of these machines, I get, how about this? Let me say it this way. I get the most questions when somebody is in a low ambient state or condition and they're trying to maintain oil control on their screw compressor. That's where most of the questions I get around that come from. And it has everything to do with the velocity of the refrigerant, maintaining DP correctly. And it's more than just DP, okay? I know I hyper focus on, and by DP I mean differential pressure. I tend to hyper focus on that a lot, and many times that is the main issue. But there are circumstances where we could technically have differential pressure, but we're not maintaining velocity of the circuit the way we need to, right? And they kind of go hand in hand. This is where things get real kind of fuzzy with how we expect them to work. So anyway, the short answer is yes. What you see, from the way I understand it as best I can, what you see with Train using the variable index, that's the same process of what York is using on their machines, and they explain it the same basic way, to my understanding. So, good question though. All right. Hope everybody's having a good week, a good time. I just hope it's going well for you. Things are quite busy on this side of things. Gearing up for the in-person class coming up in March and April. There's a lot of stuff to get ready and prepare, start working with everybody. So if you do want to get signed up for that, I do recommend like try to get in touch with me as soon as possible, because those seats, you know, they're filling up, right? And last time they also they booked pretty quickly. So granted, we had a short window last time, so this time I'm trying to give everybody more time to get enrolled, make your travel arrangements, get everything in order. So that's going to be in Houston, Texas. Again, if you are interested in that, feel free to email me at hvactime@hvactimetx.com. From there, we can work out the details, and I can give you more information on what the class is going to look like and just what you need to know. So yeah, things are getting ramped up and busy. I'm hoping in the next few months I'll be able to move into a new office, which would be great. I have lots of ideas on how I want to improve my setup here, and I really want to get basically like a prop shelf, if you will. And I'm thinking in my head, like one side have like different props and stuff, the other side be like for some manuals and things. I can kind of have both, and if I want to pull something in and actually show you how to test it, like I've got an impeller here, or I've got a IGBT up there, or an EXV on the, so I've got a pegboard here in front of me where I'm kind of doing that now. So I've got some items up there that if we ever wanted to test it, I could grab my meter real quick, which is over there technically. I normally keep it right here. I just haven't put it back up yet. Anyway, so I could grab a meter, pull it down, show you how to test everything, right? It's kind of, I want to get that more built out, and I want to improve the overall setup. So I'm hoping that that's something we can do in the new office, and yeah, just make it nicer, make it more fun, make it more utility and intentional with how we're doing the stream here. It's been a great time. Okay, so let's see, the York Titan OM. I wonder if I have any pictures of that. To answer this, let me see if I can actually find a picture to show you. I think I have some. I think I do. Just give me a second here to look through. Because if I could show you one, it would do a lot to kind of help communicate it. Because if you've never seen one, now I'm assuming the question is coming from like you've currently got one you're trying to work on, right? So I'm assuming that, and they have the same basic functionality as any chiller. They're much bigger. They do it on a whole nother scale. All right, so if I have one, it's going to be right in here. Let me see if I have one I got a good shot of. Is that one? No, not that one. Yet. Well, that stinks. Okay, I don't have a good picture of one saved. I need to do that. I can go save one, or get it in my file system where I can quickly reference it. Anyway, so the OM series is a custom line that they build, York makes, that is highly tailored. Now, so these are the machines that when we start talking about, okay, York has an 8,000 ton machine, these are the machines we're discussing. I think they start off somewhere between 3 to 5,000 tons, somewhere in there, and they can scale up to the, what is it, 8,000 or 8,500, something like that is what they're supposed to be on the top end. I guess I could try to look. I don't think I. No, I'm not going to kill time with it. Long story short, with these, the compressor will typically be on the ground. These will be a external drive compressor. I think Carrier also has a version of these machines. I don't remember what their identifier is. I know, but York refers to them as a Titan or an OEM. So you'll have the compressor on the ground, and you'll have the suction pipe. So the evaporator and condenser will still be stacked, but your suction and discharge pipe will actually pipe down into the compressor. They look kind of funny compared to what we normally expect. We normally expect a fairly tight machine where we've got a short suction, short discharge, kind of like the one you see behind me. That's a YK, right? That's a very, what we would consider a normal look for a centrifugal chiller in today's market, right? Well, these OEMs are very just like, they just look odd compared to the smaller tonnage machines that are more kind of a central package. So these OEM machines, the compressor and the oil sump is built into one main package on the machine itself. So that's something to be aware of, is like your actual oil sump, or at least, yeah, for the York specifically. Some of the others may do it a little bit different, but York has their oil assembly built into the compressor housing, and then you have your suction and discharge gas coming through and out. Um, and most everything else about the process with those is the same kind of basic thing. You have the condenser on top that flows down into the evaporator through its metering valve, comes back into the compressor, makes a solid loop. So it's a open drive coupling between the motor and the compressor. You've got a shaft seal, which is one of the more common repairs on those. So you've got a shaft seal assembly. You've got to have a motor aligned. It's all on a. It's all. It looks almost like a. Imagine the compressor being on a pump skid, right? How you would walk up to see a like a Tico water pump on a skid, right? You've got your pump, you got your motor, and your coupling. Well, think of it like that, except scaled to a 8,000-ton centrifugal compressor. That's the same basic concept you're dealing with these OM machines. It's just one big compressor skid with the compressor and the oil assembly kind of bundled into one, and then um, you've got the motor, and there are other manufacturers, I think, have the oil sump assembly as a separate component to the side, because they all kind of make a similar version of this same thing. Um, Yeah, if I had some schematics and more to show you, and I don't know if you have a more specific, I sh I'm still working on collecting all my schematics and stuff. I don't have everything fully consolidated the way I want to. It's been one of those long-term projects I've been trying to kind of chip at as I go. Those specific machines I don't have, I say that. Did I do those the other day? Here, let me actually check one other folder, because it just dawned on me that did I grab those? I may have grabbed those. One second. I did not. Okay. I did. Yeah, I didn't. Nope, not here. Yeah, it's a 19XR. Not that one, not that one. 1919. Yeah, I haven't got it yet. So, anyway, if you have a more specific question, I can try to answer it. These OEMs, I'll be frank, these aren't a machine I've personally worked on. I've read up on them. I'm aware of them. I call it familiar with them without actually having serviced one myself. I haven't. Um, but they're ultimately like, they're a bigger scale. It's about understanding the fundamental layout, understanding how York is using that compressor, getting your alignment on that compressor is critical. But so it's the same thing with a YK, right? Imagine their compressor assembly. I'm very cautious to compare this to a YK. The drive assembly is how we have to line up a YK in order to align the couplings to connect the open drive and the D housing, right? That same basic process is critical with a compressor like this, as why we go through shaft seals. A lot of times it is alignment that becomes now surging and stuff like that is also an issue, but how well you can get that compressor aligned has a lot to do with how much of a problem those shaft seals are going to cause you, things of that nature. It's just a big chiller, right? It's a big centrifugal oil sump, condenser, evaporator, open drive compressor. Motor is not included in the compressor circuit, and it moves lots of BTUs. Yeah, if in terms of like, please explain just a high level. That's where I would go with it. Let's see. On this one, so without having more info to go off of, we can just kind of talk about this from a high level perspective. And this is something you'll see. Again, that's another one. I've got pictures of this. I don't have them where they're saved. I can't get to them quickly, so I would have to. It would just take me too long. I need to get these, but yeah. So you'll see situations where you'll literally have the oil sump on. Now this is specifically going to be a centrifugal machine where it'll condensate or even potentially be freezing. And this comes back to the eductor return circuit, because keep in mind on these centrifugals, our oil system is in the low side of the system, low pressure side of the system, and so that we also have our oil return circuits going straight into our oil sump assembly or oil tank, right? Depending on manufacturer definitions or terms they use, it's all the same thing. Sump, reservoir, tank, they're used interchangeably, just depends on who you're working on. So with our sumps like this, I'll start off with using the YK example. If you're on a YK, if you start running too high of a liquid level in the evaporator, you'll get up above the oil return line coming off the side of the evaporator, which by the way, those come off on the inside of them, on the inside between the two barrels on those YKs. That's where the eductor line is at. That's also where you'll have your eductor filter. You'll have that's the filter dryer for the whole machine, and where your oil return solenoid and stuff is. All that's on the back side of the sump. So if we get too high of a liquid level in the evaporator, we get up above, or the oil latent refrigerant gets too high, and we get to the point where the eductor return line is literally only pulling liquid refrigerant back in. And as it pulls that liquid refrigerant back in, we start overloading the eductor circuit, because part of what happens with the eductor is the discharge gas we have coming from the condenser. Part of his job is to vaporize the liquid refrigerant that is being drawn in through the eductor line, which is why we have to pay attention and make sure that we're feeding refrigerant correctly through the eductor, because we can overload it with liquid refrigerant from the evaporator, and that goes directly into our sump. And so what you'll see on like a YK is if you're overfeeding liquid into the sump, you'll see the sump, your oil temperatures will start running lower, and you'll actually see the top of the sump housing in some cases begin to sweat and even ice. Like I've got pictures of this where the sump is actually iced, and you can see it. And man, I wish I know it's going to take me a minute to find the pictures. I wish I could show you this. Maybe I could do a follow up on a different stream. But that icing is a symptom of overloading the eductor with liquid refrigerant. And we see the same exact thing on the Train CVH series. So if you didn't know, the Train CVs, you're supposed to field set the eductor flow from the evaporator. So at the evaporator where the eductor line or the oil return line connects, there is a service valve there. And it's so freaking common, just people just don't know. I'm guilty of this too, by the way. I didn't know in the beginning. It's something I learned later. The If you open that valve's not meant to be opened all the way. It is an isolation valve, but it's not meant to be opened fully coming off of the evaporator. It's only meant to be, what is it? They say what is that? A quarter to half turn to a maximum of 2 turns open, and you're supposed to manually set that oil return valve on the train centrifugals, so that you limit how much of that liquid refrigerant is getting pushed in. And what you'll see as a symptom, one of two things is happening when you see the eductor block and the oil return filter, which is a filter dryer. Okay, so that's where your dryer is on the CV system, is there in the eductor line. That's what the big canister looking thing is, that's in series in that circuit. When your eductor and that filter block begin to ice over, it could be that the filter is beginning to clog up. That's something to be aware of. If that is true, then you're going to see a lot of oil migration issues, just because you're not flowing correctly from the evaporator to return your oil. So that's something to look for. But most commonly, it's not because, in my experience, what I've seen with it, it's not because of the filter is clogged. It's because we're overfeeding the eductor assembly from the oil line or from the evaporator oil return circuit, because that valve is open too much, and we need to go close that valve down a little bit so that the eductor block stops freezing. So that's one of the just between those two models alone, like two examples of what you'll see when you start seeing the eductor or the sump, the tank itself, begin to condensate or actually ice over and sweat, anything of that nature. In my experience, it has always been because of the eductor system or the oil return system, and we're bringing too much liquid refrigerant back, and it's overloading the circuit. All of that is starting to chill or put liquid refrigerant directly into our sump, which results in ends up resulting in one, will run lower oil temperatures. It may not get so low that it trips off. Like I've seen that where the oil sump temp is actually maintaining, but yet the top of the sump where the oil is not making surface contact is cold and sweating, or literally having ice form on it because it's so cold, even though the oil temperature itself down below is technically maintaining temperature. It's really weird to see, but like that is that symptom, right? So on the YK, we need to get our liquid level under control there, as an example. Or on those CVs by Train CV series, like you need to go close that eductor line off a little bit and calibrate that oil return, which you can do with it running. With it running, if you're seeing that, go over there and check it. And what my personal go-to when I see that now is, my first thing is I go over, I close the valve completely, I count the revolutions, like how far did it go. When I run into this, typically it's wide open, like all the way out. So then I'll fully front seat it, and then I'll come back out maybe one full turn, back out open, and just start there. And the only reason to go more than that is, like, if we're seeing oil migration, like we're not seeing the oil return the way we need to, then maybe go another half turn, something like that. That's going to take time to develop. So you just got to let the machine run And over a period of time, if you start seeing your approach values increase, you start seeing your oil sump levels drop, those will be the conditions you're looking for to know that, okay, I'm starting to stack oil here. Let's open that eductor line a little bit more. Let's get that oil coming back and like continuing that process. So just from a high level perspective, and then you added to that why the solenoid valve is installed on the oil sump. So Train specifically has on the machines that do not have a liquid refrigerant pump, there is an isolation solenoid that activates for a tank vent line at startup, and it's only right there at the startup period that solenoid is activated, and then the rest of the operation it is deactivated. And if I don't remember if I think if memory serves, that valve is normally open and we activate to close it momentarily at startup. And then after startup, we open it back up, or we de-energize, which goes to the normally open position. If memory serves, because it's not a normal valve. Because I remember running into this. It wasn't a normal valve. And I think it's normally open, not normally closed. So activating the solenoid actually closed it for startup. And again, that was, I think I had a train guy tell me that those were only used on the versions that did not have a liquid pump. And then like if you're dealing with a YK or something, those have the eductor system is only energized after we get past startup. So the machine's going to come online, stabilize, everything get to normal. Then it energizes the solenoid for the eductor and opens the line up, and we start allowing oil return from there, right? So if you're working with a YK system, that's why you're going to see on the sump, but the vent line from, so there's two other lines on the YKs. There's the drain line coming out the bottom of the compressor, and then there's a vent line tying into the suction eye of the compressor, which is meant to draw any like refrigerant vapors back off out of the oil, and it keeps our oil sump at a lower pressure compared to the evaporator, right? So we want that oil sump to be our lowest pressure point in the system to keep that oil there. Anyway, those don't have valves on them. So if we're discussing a different machine or something, I'll just need a little more clarification on that. Any special tips, advice for ensuring reliability on a Smardt water cooled with turbocor? I'm thinking. Anything special? I mean, we have all the standard stuff, right? So maintenance, control your approaches, make sure your GPM is there. So those are just kind of general items that are going to be true to these. And those run the kill text controls. Let's see. Because turbocor likes to run between a 1.8 to 2.2. So like if you can hit the 2.0, 2.1 compression ratio, like they'll sing all day. So if you can maintain that, so that's one thing we're looking for. Those Smarts also run liquid level sensors. I know that I haven't had too many issues personally with them, but really maintaining that liquid level control is pretty key on these. Which again, it's not really all that specific to Smardt. It's something where just all the machines that use liquid level sensors is kind of the same thing. Nothing special. How about that? Nothing special to those machines come to mind. If your machine doesn't have a, now this is going to be more of a turbocor thing, less of a Smardt thing. I know Smardt will ship these with a liquid pump option for the cooling line. If you don't already have that, that is something I would recommend considering, especially if you're dealing with a smaller loop. All right, so your loop water volume is smaller, which means you run a lot higher risk of loop inversion. Right, so smaller loops. This is something I've struggled with on some of these small water cooled centrifugals, mostly turbocores. And this is not specific to Smardt. This is just in general. They're they're commonly quite small machines, not all of them, but a lot of them. That's kind of where they caught their groove in the market. And a lot of those small loops, they don't always have buffers, like buffer tanks, to increase our water volume and to give us enough actual gallons in the loop to have a stable flow or stable operating temperatures. So when you have a smaller loop, the loop is far more sensitive to fluctuations. What that ends up leading to, in my experience, is we tend to get inverted really easily. These turbo cores, what they need, I think of this in terms of saturation. There is an actual pressure ratio that we need. Is like what, 1.6 or something. I think it was like 1.5, 1.6 minimum ratio in order to move liquid refrigerant. But ultimately, I think of it in saturation. So what I found was I had to get my saturation about 10 to 15 degrees separation, or even my water temperatures for that matter. All right, so until my evaporator or chilled water temperature was about 10 to 12 degrees below my condenser water temperature, I would have trouble getting the liquid refrigerant to feed into the compressor for cooling. So, like from a cold start, you could get about, I don't know, 60 to 120 seconds maybe out of that compressor before you start running into inverter overtemps. That's the primary alarm I always dealt with. Um, and then after that, like once it overheats once, the from there forward until it's able to fully cool down, you're looking at maybe 20 to 30 seconds of runtime per cycle, right? So if you're trying to correct for an inversion, that's what it's such a pain. So the solution for that is having a liquid pump on the cooling line. And the way that, let's see, I've seen this done two ways. I've seen it done where it would engage the liquid pump all the time, so it was always running if the compressor was calling, and it was always feeding liquid refrigerant from the bottom of the condenser up to the compressor. Or I've seen it done where there was a bypass circuit, so the liquid pump, like if the control system saw that there was an inversion on the loop, then it would engage the liquid pump until the inversion corrected. So once we had reached our set points and we come out of inversion, it would shut the liquid pump down and then run through the bypass, and the bypass had a check valve in it. So it worked very similarly to how the Carrier 30HX and GX external oil pumps worked, where they came on right as the compressor was starting up. Then as we established differential pressure across the machine or across the circuit, it would shut the external pump down and then run on the bypass circuit from there for oil flow, right? So I've seen it done both ways on those. If that's not something that they already have, is that liquid cooling pump, something to consider. They're not that hard to put in, and most control systems, and I know that like Smardt has a built-in control logic for that pump or for an output for it, because I've pretty confident they can, as an option, ship those with it. So if that's not there, so that's something, I guess, kind of specific or special. But again, that's a turbocor thing. Smardt, while I'm not a crazy fan of the Kiltex controls personally, that's just personal preference. They're fairly simple machines. That's one of the good things I'll give Smardt. They're simple machines. They didn't overthink it, didn't overcomplicate it. Whether I like their controls or not, they do work, right? Smardt machines do just work for the most part. And so yeah, nothing nothing special, I guess. We've had multiple YKs that we had to bypass the harmonic filters because they failed. The JCI contact, we have said it's just an option and isn't necessary. It's an option on, ooh, well, depends on the machine you're working on. Let's talk about it. Give me 1 second. So one clarifying question I have is, I'm assuming we're discussing, you said YK. All right, so we got that. So YK is probably a smaller YK, I would assume. So when I say smaller, your motor horsepower is going to be what, the 500, was it 503? The 503 or smaller horse. I guess that would be true even for the 700 up to the 1000 horse. Because once you get above, was it? It's either the, was it 900 or 1000 horse drives, you start getting into the floor mount panels. Do you know what your horsepower is? It won't really change my answer much. It's just more of a curiosity. Was that red doubles? Their style FG with VSD. Okay. So you've got a G series. Do you know your horsepower by chance? Again, just it's more of just a curiosity. It's not critical to the answer. Now, so I'll dive off into this here. We have multiple YKs that we had to bypass the harmonic filters because they failed. The JCI contact we have said it's just an option and isn't necessary. Any experience with issues, leaving them off. Have I had issues? No, I've not had issues with it. And especially these smaller tonnage, smaller drives, it's my experience is it's more common to not have the filter than to have the filter. Now, keep in mind, even without the filter, you still have a line reactor. And that's why they say that you can still function without the filter, because as long as you're even though you're removing because I'm assuming you're only removing the harmonic filter circuit, but you're not removing the line filter itself, which is going to be between your power input and your drive. And there is different versions of this harmonic filter. Okay, I'll get into a little more of those specifics here in a minute. But keeping it to the basic version, which is what a lot of the more, call it smaller machines, so let's say 1,000 tons and down, right, 1,000, 1,200, somewhere in there down, they use the version of the filter that they used. Like, it wasn't necessary, like they told you, it was an option. And what it does is it's helping filter. So maybe you know, or in case anybody else isn't familiar with this, so the purpose of the harmonic filter is to clean up the input and or the line side of the power coming into and feeding back out of the drive assembly. So our grid has a lot of static noise in it, just in general. Like, so it's not a overly clean power source feeding into our machines, which our drive assemblies we have today really need that clean, stable. Like they how about this? They perform best. The cleaner the sine wave and the power in is, the more stable and more efficient the drive assemblies are. So the when we have super dirty, staticky uh, power feeding into our drive, that's when we're seeing a lot of just kind of random faults at times, or we're seeing increased failures of our SCRs or capacitors, things of that nature are happening because of that dirty power. So that's something to be aware of. And this is also true for small drives, right? So based out of Austin, Texas, we have a really dirty power grid out of Austin. It's horrendous. And it is routine to constantly have to replace drives, just regular like Danfoss VLTs or an ABB 550, 580, like just standard drives on like pumps or air handlers, things like that. Those are routine replacements because they're getting fed dirty power, and while they've gotten better with time, they have better internal filtering than they used to have. It's still not enough to really clean up what they're being given. So it leads to routine failures on those drives. Same thing is true for these larger drives we're using on these centrifugals and such. Now, the whole point of the harmonic filter is to help compensate for that and to get us an even cleaner source. But the line reactor that we already have as a default component, which has to be there, already does a lot of that. So you'll also see it referred to as a line inductor, line reactor. They're the interchangeable terms from our standpoint. I've had people get super technical with me on this, and there are cases where it matters depending on what sector of the world you work in. But from a general standpoint, us as guys working on chillers, it doesn't really matter to me which you call it, because you'll see manufacturers call it both ways. Some of them will say reactor, some will say inductor. Either way, that needs to be there because that inductor core is inducing a lot of that static out of the feed coming into the compressor. But keep in mind that our the rectifiers, so with older drive assemblies, you will see you'll see the SCRs being used as our rectifiers. As our drives become more, call it advanced, I guess, we're starting to use IGBTs more and more for rectification coming in from the grid. So keep in mind, our drive assembly is bringing AC in. We then convert that to a DC voltage feeding into a capacitor bank, then reconvert that back into an AC through a set of inverters, which are IGBTs, leaving the drive assembly. So that rectification process ends up actually creating a lot of backfeed static that can get into the grid. Now, these drives have reactors in them to try to not only filter the static noise coming into the drive, but also clean up the static the drive is creating. So if that reactor isn't there, there are situations where that drive can cause a significant amount of backfeed static into the main grid for the building, and that can cause all kinds of other things to start freaking out. It can affect other drive assemblies. It can affect just other power sources. Like it's static noise in the electrical grid, right? It is what it is. It creates problems and failures, and our equipment doesn't want that. So, That's what the line reactor is doing. And then the harmonic filter is taking that a step further and further filtering those to try to clean them up more and purify them more so that we have a cleaner feed in. So for the machines where it is an option, yes, you can remove it if it fails, and it will function just like the other machines that didn't ship with it from the factory. It's fine. This changes now. This goes beyond your YK. Okay, so when you start getting into the YZ and YMC squared models, we have the next generation of drives in those, and those are far more. Those are a lot. They're a lot more advanced, and those also the newest ones, from my understanding, have the harmonic filter assembly. It's different, first of all, and second of all, um, uh, it's got it's a built-in feature. So on the newer drive assemblies, it's not an optional thing. It is part of the core assembly. I don't know on those new ones if you could even bypass it if you wanted to. I know on the older ones, like you remove the components themselves from the electrical circuit, bypass it on that scale, and then you can disable it in the configurations uh, on the OptiView touch panel, or not touch panel, but the OptiView control panel. You can just remove it as not installed, basically, is what you'd switch it to, and then remove the components electrically, and it's isolated from the system. At that point, it could have just been shipped without it. The new versions of those drives, like I said, on the mag bearing machines, I don't think that's an option. Those are a part of the drive assembly as a core, right? Um, so just something to be aware of. Again, that goes beyond your question about YKs, but just understanding that it's very likely that the YK is probably going to start seeing these assemblies that we're seeing shipped with these mag bearing systems, and it's just I think it's just where we're going to end up going personally, long term. I think I mean, they've got a lot of people don't like them. They're very complex. I get it, but that's where York is taking it. That's what they're using it, or that's what they're doing. So I do think that will roll over into their oiled YK series eventually. Anyway, to just very specifically finish, as long as you're running through your inductor, your line filter, and that hasn't been bypassed, you're perfectly fine. And if it did get bypassed, I would highly recommend adding that back. And I would assume that JCI is thinking that, well, you can remove the harmonic filter components, but the line reactor is technically a primary drive component, not a harmonic filter component. Just bear that in mind. We had a 19XR in that same room that blew the line reactor soon after. So the line reactor in the 19XR blew after removing the harmonic filter? Is that what you're saying? Which then goes back to, did the line reactor stay in the circuit on the YK? Now, I'll give you a minute to answer, but I don't want to speculate too hard. But like this what you saw there is a symptom of when we have too much of that backfeed static start feeding into a grid, and they start interacting with each other with other machines. Like these are the kinds of things that can start to happen. This is why we've got to, those filters aren't just filtering input power, it's also having to filter the backfeed coming back out of our drive assemblies. We have to be very, very careful with this. Yeah, I'll give you, like I said, if you have time, like I'm curious to just kind of have the conversation. Um, I do want to find a way at some point to be able to make this like more of an actual, hey, you can call in here and kind of talk thing. I've got ideas on how to do that one day and make it a more like literal live conversation where we could you can communicate these things, and like in your situation, Red, we could literally just talk this through in a way. Instead of right now, it's just you have to try. You're trying your best to communicate this via text while I'm just spilling out like crazy. So it kind of makes some of these difficult. If there's any other questions, feel free to get them in. I would like to. I want to give time to continue this conversation because this could be important, especially if you're having failures. Uh, really want to make sure we've got a chance to kind of talk it through. But I do have some other questions in the pipeline, and then if you have questions, anybody else on the stream, like feel free to get those in. Can't speak for certain on that the line reactors weren't bypassed. It was an after hours situation, but seeing if it's worth looking into more as the YKs have been running fine. 19. Okay, so the 19XR line reactor went out not long after bypassing that harmonic filter. So that's where I would look into that further, personally. Like I said, my main thing is just make sure that line reactor is in the circuit, right? Just make sure that it's in the circuit and it didn't get bypassed with the rest of the harmonic filter components. As long as that's in the circuit, then it kind of is what it is, and you did the best you could. I don't think it's a coincidence that 19XR popped not long after removing the harmonic filter on the YK. Personally, I don't have all the data and the information. I'm not there, but to me, I don't think that's a coincidence. So it's just something to think about and be aware of, and I would investigate personally. So, um, yeah, great chat though. I would love to hear a follow up on that, by the way. So as you kind of dig through it and learn more about the situation, I would it'd be great if we could kind of get a follow up and just see where it went, see what happened. All right. Let's see, we're gonna working on the next question. Okay. Just a second here. Okay. This one is also about a YK. Question. I ran into a scenario today with a YK machine where it was going into a stall state without high lift. Actually, there was very low lift. The condenser water at low temp around 55 degrees Fahrenheit. I thought stall happened when the lift was too low, and surge happened when the lift is too high. Am I wrong about this? I am new to centrifugal world, so any info would be appreciated. So there's three states that we could have in the context of this question. So one would be surge, okay? One would be stall. Then the other is choke. Now give me just a second. I'm going to pull up a graphic here, and I'm going to explain the stall and choke lines for these centrifugals. Okay. So something to notice here. We have a surge, we have stall, we have choke, we also have speed. Most of our YKs today, I default to, okay, you've probably got a variable speed, all right? It could be constant speed, but most of them nowadays are variable. Surge, just from a high level, let's just be real clear on what we're describing here. Surge is when we exceed the impeller's ability to move refrigerant due to how much of a difference there is across the impeller in terms of like a pressure difference. What that results in is a reversal of flow through the impeller. So with the refrigerant from the discharge side, the impeller still maintains RPM and its rotation, but the refrigerant literally just reverses back into the suction, and they equalize momentarily, and then it's able to reestablish flow and goes back. And now when you have constant repetitive surges, that's what's happening is we surge for a moment, and then it comes back out of surge after it equalizes some, and then it starts to build pressure up again very quickly, and then surges again, and we get into this back and forth. Stall is what's happening just before we actually enter into a surge, okay? And I'll actually pull my example down here. So looking at an impeller, this is our suction eye, this is our discharge side going into the diffuser. So as this is running, we get too high of a lift given the conditions, and we backflow. That's our surge. What can also happen in a stall is as we're spinning, we'll get into a spot where we'll have some of these veins will stop flowing refrigerant through them. Okay, so quite literally, refrigerant is flowing through most of these others, and it's being sent out into the compressor. But then we'll have some of these that won't be, right? So we'll use this one as an example. This particular vein of the impeller stopped moving refrigerant while it's rotating. And more specifically, they call this a rotating stall because what's actually happening is, let's say surge is a accumulation of instability, which then leads to a reversal of flow. Stall is a more pinpointed section. So let's say right here, the impeller started struggling inside of the volute and the diffuser right here in this section. The rest of it was still stable and flowing. So as we're spinning, what's actually happening is whichever vane aligns right here is the one that's actually stalling, and it's a rotating stall because the stall is correlated to, there's the word, the stall is correlated to the spot in the diffuser that is having trouble. And then eventually enough of the, like, the worse the stall gets, like we have more eddy current or more turbulence here with eddy currents, and eventually enough of this kind of builds up and instability forms and a surge happens next. So a stall precedes a surge. Now this can happen extremely rapidly, so we could go straight from normal to surge real fast, and there's technically a stall moment in between there. But we also have conditions to where we're not actually surging, but we push up into a stall state where we have certain vanes that are not moving, and that creates imbalance. That's why in a stall we can hear a stall, because it sounds like it's not quite a bearing noise, if you will, but there's just this low end grumble happening from the compressor, and you can feel more vibration when it's happening, and that is the machine is sitting in a stall state. That's where all that grumble is coming from. And that's because each of these points throws the impeller out of balance. And so right here, as it's rotating, and whatever vane is lined up with this spot of the diffuser, that is where the imbalance is coming from. And then as it leaves that and begins to flow again, it rebalances. But like, that's our stall. Now a choke is when we have really high flow but too little lift. This is a situation where the refrigerant flow becomes unstable as well, because we do need to maintain some lift in order to get the impeller to work properly. And I'll admit, I struggle. I'm still trying to find a clear way to communicate what choke is and how it's different, because these symptoms are similar in many ways, while it's technically not the same thing. We are choking the impeller versus having a surge reversal of flow. It's just, I'm still trying to figure out how to explain this in a way that makes sense. Anyway, a choke is on the other side of that. Now, if you look, we have lift, we have flow. Okay. Depending on your condition, coming back to the question, so we're pointing out that we actually have a low lift condition. We know we have low lift because we have really cold condenser water coming in, which for a YK can do, YK can do down to, I know, 60. I don't think a YK could do 55. I would have to verify that. I know that there are a lot of machines that can do 55. I don't remember if a YK can. But here's something to keep in mind with this. And Trane has a similar thing where we have to maintain a minimum lift in order to, one, we're trying to avoid choke. Now, if you read through Trane's literature, Trane explains that if they're more concerned about oil flow control, because if our lift gets too low, it means our differential pressure drops too much, and we start having oil flow or oil management issues within the machine, and we'll start stacking in the evaporator and then cause all kinds of other problems. So while a Trane CV can run down to 55 degrees, that is in their literature, you have to still maintain a certain minimum ratio across the compressor. Otherwise, you will start running into issues. I would add to what Trane explains is more than just having an oil control issue, you start pushing into choke territory. Okay, so that's the other side of that equation. But so we know we have really low lift, and you don't specify specifically how much load we have in this condition. And the amount of load has a huge part to play in this, because if we come back to our diagram, so we can discuss it from a lift scenario, and we can discuss what lift to speed means. But our flow has a huge part, like lift and flow are the most critical parts of this graph, and the speed is just kind of a subsect of it. So flow could be correlated to your actual inlet guide vane position. This is where if there's a refrigerant charge issue, or if there's a guide vane issue, things of that nature, all of those things affect your flow through the compressor. So that's what we're having to maintain. So if we have high flow but low lift, guess where we land? In choke. Now, there are scenarios where we could have a low load, so we're derating the compressor and have low lift, but if our flow still gets low enough and our speed is low enough on the machine, we can still push into a surge state even at lower loads. It's still possible. So from your point of, we have low lift but I'm still surging, it depends on the conditions. It depends on refrigerant charge, depends on what your evaporator liquid level is maintaining at, which you can see in the sight glass. Depends on the condition of your impeller. Like if your impeller has any damage, it's going to struggle maintaining a lift at that point as well. So there's just something to think about. And those are some of those things you just can't. The only way to answer if the impeller has damage is to open up the compressor. That's maybe a bit overkill given our circumstances, right? So just bear that in mind. Let's rule out everything else first. It would be the goal there. But even if we have, because if you've listened to me talk about this, you'll also hear me talk about, as long as we have lots of load, right? So what do we qualify as load in this scenario? Well, it's our temperature differential across the evaporator. That's what we're paying attention to. So we really want to make sure that we have a high enough TD across the evap, which if our GPM is correct, that means that we've got plenty of load. So if we're talking a machine designed for 10 degrees and we're running at least 8 to 10, we've got lots of heat to put into the machine. Compressor can really open itself up, run wide open. It's going to run great. And under those conditions, with a really good load, we could handle really high lifts. We can handle, right? So you could run some significant lifts across a centrifugal as long as it has enough load input into it. And you can see that on the graph by as flow increases. And then, so if we come over here where we've got high flow, we can run some pretty high lift, right? And this graph, mind you, is not perfect. It's just kind of a representative, but this is similar to what a surge graph will look like for a centrifugal. Now, you can still push up into a surge here, all right? Just bear that in mind. But the point is, high load, you can manage high lift. But we have the opposite scenario where if we have a high load meaning flow, this term flow is directly connected to how much load we have. The more heat we're trying to process, the more flow we're going to have through the compressor. Okay? So just understand that. Your flow is directly tied to your load. So if we have a high load, but then we drop that lift, then we get into our choke, which can mimic, or it shows similar symptoms to a surge. Now, it's very easy to get mixed up with the terms here. Okay, so surge and stall are over here on this end of the system where we're running lower flows but high lift. Choke is on the opposite end where we've got low lift with high flow. And we want to stay in this middle zone in between here. Now, one way that we could have, let's just assume you've got low flow. All right, so we've got a low load, but we've also got low lift. Something else that comes into play is if we've got a variable speed machine, as we reduce the speed of the compressor, the amount of lift we can maintain lowers. This is why that when a variable speed centrifugal begins to surge, it increases speed of the motor. Now it may close the inlet guide vanes, but the motor itself will speed up. That is true with any centrifugal that's variable speed. The reason for that is because we want to get how much lift we can handle higher. And we could go way off into the weeds on the relationship between IGV, speed, lift, and flow. Like all of these are correlated in a very, honestly, complex way. Like it takes a lot of thought to really think through how all these impact, because all four of those like move this dot all kinds of places, and it depends, right? These are things I go into very in depth on with my certification course at chilleracademy.com. I'm just saying, like, if you actually want a really good solid breakdown of all of these things and how they affect each other, how they interact, and you really want to dive into that on a deeper scale, that's where to do it. I took all the time to explain all this into detail. It would take a lot of time to try to do that today, so I'll just try to keep it as high level as I can. So if our compressor is running at its minimum speed, so if you've got low flow, low lift, so you have a low load with low lift, but that also could mean on a variable speed compressor we have a really low RPM. That's where we say, okay, it's possible, especially let's just assume maybe the liquid levels in the evaporator aren't quite balanced perfectly, or in the condenser, maybe our charge isn't quite perfect on the machine. That could send us right into a low end surge. This is what they would call it. So you've got low end surge, high end surge. All right, so high end surge, you've got a high load scenario, high lift, and you surge. Low end surge, you've got a low load, maybe lower lifts, but yet you still push into a surge, right? So when you hear those high end, low end surge terms, which are just kind of field talk in my opinion, I haven't seen literature that uses terms in that way. Anyway, when you hear that, like that's what's being described. So this is possible. Whether you're actually surging or whether you're going into a choke is going to depend on how much load you have. Kind of just coming back to that, and just that's what I'm focused on here, and just be aware of the fact that just because so what you've done is you've done condenser relief. All right, so we can relieve our machine by running really low condenser waters, getting our lift significantly down, which decreases the total horsepower required or the watts needed in order to move the refrigerant from our low pressure saturation to our high pressure saturation. So as we reduce the compression ratio, aka the lift, not the same thing, but same kind of concept, right? As we reduce that, we save energy. That's what you've done by going with a 55-degree condenser water temperature. But there's caveats to using those low temperatures. They can't just go there in any condition. You have to use that correctly. And that's part of what we have to be careful with is, and these are oiled machines, right? So keep in mind that mag bearings mag bearings can do this in ways that oiled machines can't, because of not having oil in the system. They heat exchange better because, again, there's no oil to interfere with heat exchange. And it's possible that if you're not running a minimum a minimum lift or ratio, you could be stacking oil in your evaporator because you're not able to return it properly. And it may run like that for a period of time just fine, and then it suddenly starts having surging issues. And what I would expect to see then is your approach probably increased. Now keep in mind though, your approach may have originally been half a degree, 1 degree, and it may not be excessive approach, right? So in this scenario, when we start having that oil interfering with us, as we start seeing it stack in the evaporator, it may not mean you're running 4 or 5 degrees plus approach. It may mean you went from 1 degree to 2.5, but nothing else changed. You just saw that approach value slowly increase with runtime, even though the load and everything else stayed relatively the same. That's the symptom you're looking for if you're beginning to have migration due to having too low of a lift. So this is why we have limits to this, and we can't just go to the extremes just to try to maximize efficiency. And bear in mind, like, so this is what our role as the HVAC tech on site becomes in this scenario. The controls guys don't know this stuff. They don't understand this stuff, especially if they're a young controls tech. And they're taught condenser relief. They're taught like these advanced control strategies and stuff. And same thing with the facilities personnel too. They're taught what these things are. And you'll hear even myself advocate for this. You'll hear other guys online. We advocate for, hey, let's get some condenser relief going here. Let's really save some efficiency or some energy on this plant. But they don't know the limitations that we have to work inside of. We can't just go full ham on this, because then we open up other problems. Otherwise, we would just try to do this all the time, no matter what, and we wouldn't have these limitations on the table for us. So our role is to explain this and to be the guiding voice of, hey, we can't do this because of this, right? And that's, yeah, not knowing, we don't have all the info we need, but despite either scenario you're in, these are things you have to pay attention to and why you're seeing symptoms. This is why you're seeing symptoms. And now we just need more information to go off of, to dive deeper, to figure out, okay, is it actually surge? Is it a choke? Either direction it is. Now we've got to start adjusting, okay, under these conditions, 55 is just too much. Let's back that off. Maybe go 58, maybe go 60. I personally don't like running my YKs below 60, was where I like 65 was really my kind of default on the low end. There are scenarios where I was fine running down to 60. It was fine, right? As long as we had good control, we had a stable environment. I never liked going below 60. And to my memory, I don't think the YK was supposed to go below 60, or maybe that was the older machines. Maybe the newer models, they say they can go down to 55 condenser water. Maybe I'd have to look that up to verify that. And there are a lot of other machines that will do 55 all day, especially these mag bearings. These mag bearings will fly down in there, but these mag bearings have the same limitations. Just bear that in mind. We can get down there and stay there more consistently with a mag bearing and have less issues because we don't have to worry about migration. But we still have to stay within our surge and choke boundaries. And those mag bearings are not excluded from those boundary zones on that compressor. And that graph changes for every compressor. Every compressor is slightly different in terms of model of compressor specifically. So every compressor model and design has a slightly different surge graph. And these are not things that we typically have access to in the field ourselves. Like we don't get those charts for most compressors. That's something that the factory holds internally on their side, but it is built into the control logic. And again, I go through all this in my course, but like these things are built into how the machine stages. And like when we have an IGV VS or VFD combo, like why we see the inlet guide vanes go full open first and then we see the drive start to increase speed. Like all of that is tied back into what that surge graph looks like and where, what point are we on that graph. All that's built into the controller, even though you may not know it's there. You don't know that that is part of the algorithm controlling that. It is still part of what the manufacturer is using to control the machine either way. You just may not have access to it. And then like there's going to be scenarios where you'll see that the IGVs only go open so far and then we increase speed and then we open IGVs more. Again, that plays back into that graph. The machine knows to do its best to stay out of a surge. And so it's going to step these things accordingly. In a perfect world, you go full IGV 100% open, and then we start increasing the compressor speed. But that's only if conditions allow. Getting back to the speed has an effect on what our surge ceiling can be, or lift ceiling, I should say. So if we need to maintain a higher lift or a higher ratio, then we have to speed the compressor up before we can open the vanes more. Is that making sense how these things are correlated and directly tied? I really hope so. This is a very advanced topic, right? This is not simple, and it takes some serious control systems to balance this correctly. So if it doesn't make sense at all, don't feel bad. Like we're getting into some pretty advanced stuff here. See, Mr. Eric Johnson. What's up, buddy? We need to chat. Are chillers being used in these new data centers that companies are spending billions on? How do you think these data centers will change the chiller workforce and the quality of techs? Ooh, coming in with the deep ones. Let's see. I kind of already read it. I'll just get this posted here so everybody can see. Chillers are the primary cooling source for these systems. Okay, most data centers, especially if it has any real size to it, are going to be chillers. And we're seeing data centers, I mean, it varies. A single data center, like, okay, so some that I know of and have participated in on some scale here locally in Austin. Like we've got 48 air-cooled 500-ton air-cooleds on one data center. Jason had a plant he did on YouTube, Jason Johnson, the other day where I think it was 20 or 40 of the plant he was at, the data center. And we can it's you can get up to hundreds of chillers all tied in to the same network, like the same piping and everything. It gets crazy how big some of these systems get and just how massive some of these data center campuses are. Like it gets really crazy. So yeah, almost basically all of these centers are chiller systems, and that's one reason why the chiller market for us is expanding. Like it's expanding so quickly, it's just hard to even fathom how large it's become and becoming, especially compared to how many of us there are. There's not. That's part of the issue I have right now. We have more data centers getting put in and being built than we have the infrastructure to support them, especially like us from a technical side. And many of the centers around the U.S. that I've been involved in trying to help them work through, like it does come back to they just don't have the freaking manpower to do the startups, to do the commissioning. They're trying to hurry and rush, and they're trying to it's a crazy madhouse right now. And you've got a lot of these green technicians who are they're just trying to keep their hair from catching on fire at this point. Like it's really what it boils down to. They're way over their head. They don't know what's going on. It's not their fault, my personal opinion. It's not their fault. They just we're having to throw everything we've got to meet the demand. everything we've got to meet the demand, and it is stretching us in a really hard way. Like, it's really pushing our limits. Um, so yes, in terms of how that will change the quality of text, we've already seen it from in terms of technician quality. We've already seen a significant, call it downgrade for lack of a better term, because of having to bring in so many green, less experienced, less trained technicians into the market as a whole. This is just the industry as a whole. The We have so many greener, newer, less than 5 year technicians in the market compared to used to, that collectively it's not hard to argue that we have reduced in total quality of technician just from that standpoint, which in my opinion a lot of it is just experience and training. These are things that will correct themselves over time. So when we talk about that same concept from the technicians servicing these data centers, that same trend is going to continue. We're probably going to have a lot of data centers for quite some time that are not done very well, and that a lot of technicians are really going to be struggling. We're going to bring in a lot of technicians who are really going to struggle for quite some time. And that's just part of that, call it bell curve, if you will. Eventually, I do think that we will see the other side of this, and we will start to rebuild the personnel we need. And I do think that, like, through training, there's going to be a lot of guys who, they would probably fit better somewhere else in the industry, and there's going to be a lot of us who we just needed time. We needed time to get in it, to develop, to become better, to study, to learn, to experience just the hardness of it. Yeah, and a lot of these guys a lot of you are out there. You don't have the same level of support that a lot of those who went before us had. We don't have those senior guys. We don't have somebody working with us. We're not working in the same apprenticeships that we used to. Like, all of that stuff isn't happening anymore, which is reflected in how good of a job we can do. Right? But again, I do think there will be a correction on this. It will be a temporary growing pain to have a lot of young technicians who just don't know better push the wrong button and break something a lot. But eventually they will learn not to push that button. And if they had somebody who was there to tell them, don't push that button, here's why, we wouldn't have to do that. But because most of us don't have somebody there to tell us, don't push that button, we have to push it and learn it the hard way. And then we realize, oh, I don't want to push that button anymore, right? That's what I think. Like, we're in that process right now. I think data centers will have more money to attract people from traditional service companies. I completely agree, and pay them at a scale that is way above what the local service market can bear. Well, I think that is partially true. I see a lot of companies who are specializing in data center service beyond just the manufacturers. See, that's something to bear in mind. The manufacturers have heavily owned this data center market for quite some time, like heavily owned. That's who they went through, as the OEM. We've seen companies become very successful specializing in data center service. I've got companies here local who have really done that and done it really, really well. And so, like, this is what they do. They service these contracts, these customers. We are yours. And those are the ones where, yeah, they're charging those higher rates, but they're giving such a good specialty service that, now, to that point though, we do see it in the market where there are there are some of these, and I work with some of these guys. Like, so in the, I have to be careful because I have a lot of NDAs on who I work with, and so I have to be cautious who I talk about. But one of them that I like, I'll give Google as an example. In Chiller Academy, I have quite a few um, tr- field trained chiller technicians who went from the field into working for Google and overseeing their data centers. Those are things that we have had happen. And so like there, that's an example of where they will pull some of that talent in house. Something else to keep in mind though, and we see this across the board, these companies because they're such big major corporations and stuff, they don't have a stomach for the liability because it's just all about the ones and zeros at the end for them. So because they don't have a stomach for the liability, even though they bring in these experienced guys, and that's no longer a field tech, they're nothing. All they are meant to do is maybe very minor repairs, or we're talking temperature sensors, things of that nature, very, very minor stuff, maybe even the maintenance. But when it comes to actual service and stuff, a lot of these they don't want, nor will they allow those guys to get in and do the in-depth service, which still ends up bringing in the third-party contractor to do that work for them. Even if their in-house guys did most of the diagnostics, and the third party guys come in and do the actual, like maybe finish it or do the work, do the repairs, whatever the case. We see that because then the service contractor takes the liability of the repair, not the corporation of the data center. And so we get into this whole liability game. So we see that, and where sure that guy could do my job. You know, the facilities guy overseeing this data center, he could do my job if they would let him. But they won't. So I think that will still continue to be a trend. I don't think that's going away. And that's even if they do pluck people from us. I've just seen this too much. I've seen this too many times where they are not going to take the liability. They would much rather somebody else's insurance take that hit when something goes bad than themselves. And then they can blame somebody else at that point. They're not having to have disciplinary on their own internal people because, well, you shouldn't have done that and it crapped out. Now they're able to hold somebody else accountable, and then like you get into the politics of this whole stuff too, right? Where these corporate managers, it's easier for them to blame a third party contractor and then to cancel the contract and go get somebody else and show to the superiors, hey, I did something, you know, these guys didn't do a good job, I canceled, I fired them and I got other guys, compared to that's a internal employee who has all kinds of labor protection, right? So now I could write him up, I could try to get him to leave, I could do that kind of stuff, but like depending on how bad of a failure it was, like I've got hard limitations on how much disciplinary I can put on this individual. So I have way more ability to do that to a third party company who does not have those same labor protections that my actual on salary employee does, right? So that's the whole politics of this game too. It it gets messy fast when you start talking about some of that. Do data center specialized companies travel a lot, or is there enough work to stay in a local market, like a few states where technicians can be home most? So the data center company, there are some that travel quite a bit, that do service on a national scale, but I'm seeing a lot of them pop up around the U.S. that are just regional based, where we've got clusters of data centers. You know, here in Texas, we've got quite a few between DFW, Houston, San Antonio, and Austin. Like we've got quite a few data centers in this cluster to where one moderate sized service company, or well, honestly, there's a handful of them now that can serve these without having to go anywhere else. They don't serve any other markets. They're just here. So I see that more and more and more. And I see that more now. You rewind that clock 5, 10 years ago, I saw that less. In that time, there was far more there were the companies that did that tended to travel more, but again, that market was heavily owned by the manufacturers. And the manufacturers just have their service offices spread across. But one of the things, when you start to get to a high level within the manufacturer, OEM like service team, you tend to travel quite a bit talking to these guys. Maybe not in every case, but a lot of these, they're like top end guys. They go all over the freaking place, and it's just part of working for an OEM. That's one of the reasons I personally never wanted to go that path, because I didn't want to do the travel as much. But it's just part of being a tech for one of them. I was trying to avoid that life. That's why I never went that way intentionally, even though I almost did at one point. I almost did. And I'm not saying that just because you work for an OEM, you're going to for sure have to travel and stuff. I'm just saying that as you advance yourself within their organization, it's very common for those top end guys to have to be on the road more than I want to be. I'll say it that way. Um, anyway, appreciate you jumping in, Eric. Really good to see you, bud. We do need to follow up. So if you didn't know, Eric and I have been trying to talk through. I've still got to figure out how to do it, and hell, we're already here in January, and we've still got some boiler season. So Eric has Boil Learn, and he runs like a lot of boiler training and stuff. So if that's something you're interested in, talk to Eric and get in touch with him. He's a fantastic guy. Really enjoy having worked with him for what it's been a year and a half now, Eric. It's been at least a year since we first connected and started collaborating and doing stuff. And we're going to do a special live stream here at some point where we do like a boiler Q&A between the two of us. Now, I'm not a boiler guy, so it's going to be more of he come on. I'll probably spend more time managing the stream and just kind of chatting. And I'll let him kind of take control of the actual questions coming in. But we'll take a boiler focused live stream here at some point. And that's something we may do at least once a year or something at some point going forward, because I've had quite a few of y'all request that without me actually we just, again, it's not right now, it's not on Eric, it's on me of just getting that organized. It's always boiler season. It's true. It's absolutely a fact. Can you explain why data centers have to plan to use millions of gallons of water per year? Are they just losing that amount of water due to evaporation? So I do need to wrap this up. I'm going to save this. I do want to talk about this, and I've heard this. I've looked into it myself. I personally call bull on most of that. The water issue is not as big of an issue. Now, this is regional dependent, and I may step on people's toes with my opinion here. But being somebody in the space, be careful who you listen to. It does matter the region you're in, but it's not what they... There are people who benefit from these data centers not thriving and having markets pushed down on not letting them go wild with their building, okay? There are people who benefit from that because they're on the other end of that market. And data centers becoming more and bigger and more of them means they get less of whatever they're doing, right? So companies will put out these studies and stuff to try to attack each other through public opinion, okay? My opinion, high level, I have much deeper thoughts on this. We can go into maybe next week. But what you're seeing in the media is you're seeing the corporate PR attacking one another, trying to see who wins, not actual issues. Personal opinion. And there's a lot more of that than I think a lot of people would realize. But to give a real quick example, there are plenty of water-cooled data centers, but a lot of them are air-cooled. These data centers that are air cooled, yes, they take a lot of water to fill up once, to get all the gallons in their system once. But that water's then there, and it's treated, and it's controlled, and it's regulated, and like it's there. It's not going anywhere. And due to reliability, that's why these data centers are putting in so many air cooleds. And you don't see as many water cooleds. So their whole thing on water cooled usage, like even the way that they're calculating this, it's so misleading. It's so misguided, and it's obvious to me that it's an attack, like political public opinion attack piece, not real data from people who actually know what they're talking about, in my opinion. I gotta go. MTT, make the time for your family, for your spouse, for your kids. They really need you. We've got to make the time. The time is not just going to be there. You're not just going to have it. You've got to be intentional with it. It is freaking hard. We have a lot of work. This industry demands a lot of us. I struggle with this routinely, trying to run this academy, even just leaving the field and coming to do this. Like, it takes a lot to support the industry that we're in. Not just from me, from all of us. Especially in a time frame when we don't have enough people to do what we do. We have to make the time for each other. Please, please do this. Please take this seriously. Let's try to find out, how do we do that? Anyway, I will see y'all next time.